Alrighty, well let's go ahead and just start on some additional problems. We have sigma n is equal to 0 to infinity of the square root of n plus 2 over the square root of n squared plus 1. How are we going to do that? Now I guess we could do ratio test, and if we do ratio test, our a sub n plus 1 would be n plus 3, and down here this would be n squared plus 2n plus 2. And therefore when we have the limit as n approaches infinity of n plus 3 square root of n squared plus 2n plus 2, and then of course the reciprocal of our a sub n, we wind up having a problem. And the problem is this. Okay, you can actually multiply those together, right? And you wind up getting n squared plus 1 and n plus 3 under one radical, and you wind up getting n squared plus 2n plus 2 and n plus 2 under the other radical. Well, guess what? That limit is 1, which makes this inconclusive. So that was kind of a dead end, okay? What are we going to do with that? Well, here's the thing. Whenever you're given something like this, imagine it without the constants. If you imagine it without the constants, that's root n over root n squared, or 1 over root n. Well, why don't I compare it to that? Well, why don't I compare it to that using limit comparison? Because I know that if I designate that as my Bn, I know that that is a recognizable divergent series. Okay? And therefore, I can go ahead and do the limit as n goes to infinity, right? Okay? And then I just have to make a ratio, right, of what? Well, I simply have to do a sub n, which is, n plus 2, square root of n squared plus 1, over 1 over root n. And if that is the case, I can simplify it. N plus 2 times root n over n squared plus 1. And using my properties of radicals, I can actually do n squared plus 2n over n squared plus 1. Now that is equal to 1. But limit comparison test, that's allowed to be equal to 1 because it just needs to be a finite number greater than 0. And if that's the case, then either both converge or both diverge. Well, if that diverges by p-series, and this is greater than 1, then the original diverges as well. So we have divergent by limit comparison. Okay? Let's go ahead and move on to the next problem. Let's do n is equal to 1 to infinity of n over n plus 1, and this can be 3 to the n plus 1. Now the question is, what am I going to do on this one? Well, there's actually more than one way that I can do this, okay? I can do this by limit comparison test, but this is just screaming for me to do it by ratio test. So if I have a sub n plus 1, that becomes n plus 1 over n plus 2 times 3 to the n plus 2. So I have the limit as n approaches infinity of n plus 1, n plus 2, times 3 to the n plus 2, times n plus 1 times 3 to the n plus 1, all of that over n, right? because instead of dividing by the a sub n, I'm just going to multiply by its reciprocal, because I'm going to wind up doing that anyway. Okay. Now, this is one more 3 than that is. So this cancels out with all but one of those 3's. And the rest of the n's sort of line up very nicely, and you wind up getting 1/3 times n squared plus 2n plus 1 over n squared plus 2n. Well, guess what? This quantity right here goes to 1. But if it's multiplied by 1/3, the whole thing goes to 1/3. That means that it is less than 1, and therefore it is convergent by the ratio test. Okay. Now, let's go ahead and let's move on to another one. How about well, here's the thing. This is actually an extremely easy one. And the reason I drop it in right here is because we've done all these ones where it took a lot of thought and you had to basically jump through all sorts of hoops and everything like that. And then we come to here and we come to find out, oh my gosh, this is convergent by p-series. All you had to do was just change the form just a little bit and just recognize the fact that n times root n gives me n to the 3/2. 3/2 is greater than 1. It's convergent by p-series, okay? So, I mean, that's the whole stop and think aspect of what I've tried to train you to do over the years. And that winds up being a very, very easy problem. But if you're just dead set on using these more complicated ones, you could actually sort of lose the. I mean, you could do it by integral, because p-series is basically just a corollary of the integral test. But why go through all of that when p-series test has actually been sort of codified for you to be used like that? Okay. All right. Well, let's move on. Let's get a couple more examples in. How about, that looks like a fun one. Okay. Well, let's look at that for a second. What in the world does that look like to you? Well, it's got factorial, so we may think ratio test. Is there anything else? Well, the factorial means that the integral test is just right out. Like, you can't really do anything in terms of integration with n factorial, right? It's not going to be root test because this has no power of n. It's n factorial. There's really nothing really similar that you can compare it to. So it's probably going to be ratio test, okay? And I want to sort of, every once in a while, stop and slow down and sort of think and let you listen to me think through this. Because like I've told you before, you know, we learn everything by imitation. We learn how to think through these things by watching somebody else's thought process and exactly how they go down and sort of tick things off. I know that if I'm going to use ratio test, it makes sense to go over here and actually explicitly write out my a sub n plus 1. So we have the limit as n goes to infinity of n plus 1 factorial over e. And I'm going to go ahead and expand this. N squared plus 2n plus 1 times e to the, sorry, it's supposed to be n squared over n factorial. Well, I know by rules of exponent, well, let's go ahead and simplify the factorial first. N plus 1 times n factorial. And I know by rules of exponents that I can split this apart like this if I wanted to. And of course, I'm doing it for reasons of being able to cancel out. This cancels with that. That cancels with that. Now, here's the thing. As n goes to infinity, I have a linear over what? An exponential. So the linear over the exponential is going to go to infinity so much faster. This is 0, which is less than 1, and this is convergent by the ratio test. Okay? Alrighty, well let's do one that's a little more difficult. Equals 1 to infinity, and you have 5 to the n over 3 to the n plus 4 to the n. Okay, well, Well, why don't we go ahead and let's change the form, because it would be easy if it were, if it were n is equal to 1 to infinity of 5 to the n over 3 to the n. That's divergent, and you just go minus 1 or something like that. That becomes more divergent. You can do it by direct comparison, right? Or, if it were n is equal to 1 to infinity of 3 to the n over 5 to the n plus 1. That would be convergent, and then making the denominator, that would be direct comparison too. What do you do here? Okay? Here is the real problem. Okay? So what we're going to do is we're actually going to multiply through by 4 to the negative n. Okay? Once we multiply through by 4 to the negative n, we're going to get n is equal to 1 to infinity of 5/4 n over 3/4 n plus 1. Okay? Well, here's the thing. This winds up going back to probably the easiest one to do. And what we need to do is we need to figure out if this goes to infinity, right? There's no sense in looking any farther. This is just the straight divergence test that you learned back in the nth term test, or the divergence test that you learned back in 11.2, okay? If the limit of a sub n going to infinity is infinity, meaning that each successive term gets larger, there's no way it can be convergent, okay? And that's exactly what happens. It actually goes to infinity, because in the numerator, that goes to infinity because it's a ratio greater than 1, right? That goes to infinity. This in the denominator goes to 0 because it's a ratio less than 1, 3/4. So basically what you wind up getting is infinity over 1, or just infinity. Therefore, it diverges by the nth term test, okay? And that's one that we fail to remember because we move past 11.2 with its nth term and its review of geometric series, and then its mention very briefly of telescoping series. And we want so badly to use all of these down here, because these are the new ones. These are the sexy ones. They're the ones that really kind of, have a little bit of pop and pizzazz. The hardest part about this sometimes is the fact that you will wind up ignoring the easy tests. So you'll make things much harder, or in fact make things impossible for yourself at times, because you weren't remembering the easy tests and you were trying to fit a square peg into a round hole by trying to force one of these more ornate, one of these more robust and sort of complicated tests upon a series that really it doesn't accommodate. Okay. I think that's pretty good for sort of reviewing these, especially since you have examples of all of them in the preceding videos. So we'll go ahead and call our foray through 11.3 to 11.7 to a close here. We'll move on in the next couple of days to 11.8 and on and start talking about power series. If you have any further questions, please do shoot me an email. Otherwise, I will just look forward to seeing you at our next Skype session. Bye-bye.